This is example problem 9-71 out of your book. This problem deals with an ideal Ericsson cycle. We're told that air is the working fluid and it's a steady flow system, so it's an open system. State 1 is given at 300 Kelvin, 120 kPa. We're told that process 1 to 2 is an isothermal compression during which 150 kilojoules per kilogram of energy is rejected. And process 3 to 4 is an isothermal expansion at 120 Kelvin. 1,200 Kelvin. All right, so let's go to the next slide. And as always, I suggest drawing the PV, at least the PV diagram for this one. I won't draw the TS, that's up to you if you'd like to go ahead and do it on your own. But I'm going to go ahead and draw the PV diagram because it's helpful to envision the process. And it helps us from getting confused as we are calculating different states. So let's go ahead and draw this. Okay, so we have 1 to 2 here, 2 to 3 here. Oops. Let's try that one more time. Let's see, here's our isobaric. Here's our isobaric process. Now I'm going to connect these with some squiggly lines. These should not be so squiggly, but you get the idea. You can look them up in your book and see what a well-drawn Ericsson cycle should look like. Okay, so let's label our states. So we have here 1, 2, 3, and 4. And to remind you, 1 to 2 is isothermal, so it takes place at a constant temperature. Try to write that a little neater. This is also isothermal. And then these other two processes between 2 and 3 and 4 to 1 are isobaric. Okay. And we know that we have heat addition between 3 to 4. We have Q in. And we have Q out between 1 and 2. Okay, so using the givens in the problem, we know that this heat rejection, so Q1 to 2, so Q1 to 2 is going to be negative 150 kilojoules per kilogram because it's heat rejected. Kilojoules per kilogram. And we know the elevated temperature, the heat addition, occurs at 1200 Kelvin because we're told that in the problem. So this is the isothermal expansion. This is the isothermal compression. All right, so now that we've drawn our system and we can visualize it, let's go ahead to the first part of the problem. The first question is, what is the maximum pressure that occurs in this cycle? Okay. And so because we've already drawn this, we know that Pmax occurs at P2, at state 2, and at P3, at state 3, because it's the process between 2 to 3 is isobaric. So P2 equals P3, and this is the highest pressure in the cycle. So let's start. We know state 1, so as our typical approach to these problems, we're going to start marching forward in terms of finding subsequent states from states we know. So we're going to find state 2, and we're going to do this using an energy balance. And the reason we're going to do that, the reason we know to do that is because a couple of things. First of all, we know what the energy addition is. So in theory, we know the stream in. We know the heat addition. In theory, we can find the stream out. Also, we have to think about what we know about the process. We know this is an isothermal process, so some of our other options, like an isentropic process, are not available to us. Okay, so let's start with an energy balance here. So it's an open system. So when let me rewrite this. Let me start a little bit earlier on in our energy balance here. Okay, so if I write my energy balance for a steady flow system, I have the change of the energy in my control volume with time. And let me do this all on a specific basis. So let me rewrite this guy here. And we do it on a specific basis because we don't know what the mass flow rate is in our system and it doesn't really make a difference. So that's the energy of the control volume, as messy as that looks. Okay. All right, so it's equals Q dot minus W dot, so the rate of specific heat transfer minus the rate of specific work transfer, plus H in, which is going to be H at 1, minus H out, H at 2. Okay. Now, we know that it's a steady flow system, so this guy goes away. And we can rewrite H1 minus H2 as Cp dt, but this is an isothermal process, so this also goes away. So what we're left with is Q dot equals W equals negative 150 kilojoules per kilogram. Okay, since this is an open flow system, we know that our boundary work, our open flow work is going to be V, the integral of V dP, and this equals negative 150 kilojoules per kilogram. Excuse me, these are, while I've put these on a rate form, which they would be in the case of a steady flow system, in our problem we're actually given these on just a net work and heat transfer basis. So I'm going to switch here at this point just to give you an alert here. I'm switching to just a total form. So this is no longer rate form. So again, if we were looking at this, if we were given the rate of heat addition, the rate of mass flow, for example, we'd be on a rate form, but we're not. So let me switch over here to just being on a total form. All right, so we have 150 kilojoules per kilogram being rejected. So what we get when we integrate for our open system work, let me rewrite this, is we get 150 kilojoules per kilogram equals the integral of V dP. All right, going to the next page. When we go ahead and integrate this, we get let me rewrite that. We get 150 kilojoules per kilogram equals R, gas constant, over the molecular weight times T, the temperature at which this isothermal process takes place, ln of V2 over V1. Okay, so we know a few things here. We know our universal gas constant, we know our molecular weight, we know the temperature at which this process takes place. So the only thing we need left in order to find V2 is V1. So we can do this using the ideal gas law. So V1 equals, so 1 right there, is R over molecular weight T1 over P1, which we're given in the problem. And so we can find V1 is 0.717 cubic meters per kilogram. Then we can plug that in, and we can solve for V2, which we find to be 0.125 cubic meters per kilogram. Okay. So our next step, we know our specific volume at 2. We also know our temperature at 2. T2 equals T1, since it's an isothermal process, is 300 Kelvin. And so now we can just use the ideal gas law again to find P2, which is what we're looking for in part A of this problem. P2 is R over molecular weight times T2 over V2. We know all these things. When we calculate this, we come out with 688 kilopascals, and that is our answer for part A. All right, going on to part B, the next thing we want to find is the net specific work output. For this cycle. Okay. So our W net out, because this is a cycle, is going to equal Q in, again all on a specific basis and not on a rate basis as I originally wrote this out, minus Q out, because we're looking at each individual execution of the cycle instead of looking at an overall rate. And we can rewrite this in terms of our individual steps. Q in occurs from 3 to 4. And now I'm going to add this again because Q out has a negative sign associated with it. So the negative and negative is going to make a positive when we write Q out on an absolute basis. So Q3 to 4 plus Q1 to 2. Okay? And we already know Q1 to 2, that's given in the problem. That is negative. Rewrite that. Again, given in the problem, negative 150. Oh, my. 150 kilojoules per kilogram. Okay, so now that means that this Q3 to 4 is what we need to find. So let's do that now. So let me write an energy balance again. Okay, so the same energy balance as we did before. We end up with, and again, making the same simplifying assumptions, Q minus W. Remember, dH is going to be 0 for the ideal gas because it's Cp dt, and dt is 0 in an isothermal process. And so we have Q equals W. Once again, W is going to equal the integral minus integral of V dP. And so when we go ahead and integrate that out for an isothermal process, we get work equals P3 V3 ln V4 over V3. Okay. Now we need to find V4 and V3 in order to evaluate this process. So let's do that now. So state 2, we already know. We've already found our state 2. We have 688 kPa pressure. This was our answer to part A. We know T2 is 300 Kelvin because we know state 1 and we know an isothermal process between state 1 and state 2. And we know our specific volume at 2, which is 0.125 meters cubed per kilogram. Okay, so now let's look at state 3. We know P3 equals P2 because it's an isobaric process between these two states. So P3 is also 688 kPa. We know T3 equals 1200 Kelvin because this is given in the problem. And so we can find V3 using our ideal gas law. And we calculate this to be 0.500 meters cubed per kilogram. All right, so now on to state 4, which is the last one we need. We know T4 equals T3 because it's an isothermal process. So that is also 1200 Kelvin. Again, this is given in the problem. We know that P4 equals P1 because it's an isobaric process between the two of them, so we have to get back to our initial pressure, so that's 120 kPa. And then once again, we can use our ideal gas law to find V4, and we find that to be 2.87 meters cubed per kilogram. Okay, so now we have everything that we need in order to evaluate Q3 to 4. So it equals, again, this was our integrated work expression. Oh, excuse me. It's going to be our pressure, 688 kPa. Times our specific volume, 0.500 meters cubed per kilogram, times ln 2.87 meters cubed per kilogram over 0.500 meters cubed per kilogram. And when we calculate that out, we get 601 kilojoules per kilogram. So now we can calculate our net work out. And we calculate that to be 601 kilojoules per kilogram, 3 to 4, minus that heat rejected from 1 to 2, 150 kilojoules per kilogram, and we end up with a net work out of 451 kilojoules per kilogram. Okay, and then finally part C of this problem asks us what is the thermal efficiency of this cycle, and we're going to use our standard definition, which is net work out, what we're trying to get, divided by what we have to put in, Q in, and so this is 451 kilojoules per kilogram over 601 kilojoules per kilogram. Oops. And so we get 0.69 or 69% efficiency.